5.4, analyze graphical models. So example 1, amount of bacteria left. When someone has a bacteria infection, what they do is they take medicine and the bacteria begins to decay in their bodies, making them gradually feel better and better. Suppose that dish A is infected with 100 bacteria and dish B is infected with 200 bacteria. Okay, so two different situations here. After adding medicine, both types of bacteria decay at a rate of 20% per day. Okay, make a table showing the daily number of bacteria in each dish for 1 week. Okay, so 1 week is obviously 7 days, and the decay rate is based on the number of days. Okay, determine whether the pattern is best represented as linear, quadratic, or exponential function by calculating first differences or second differences or the ratios. Okay, so we're going to do the first one. So 100 bacteria. Okay, and then what we're going to do each time is we're going to go 100, or like the number, times 0.80. And the reason why we're going to do that is because it decays by 20%, therefore 80% is left. Okay, so the next one's going to be 80, and then we're going to say 80% of 80, which is 64. And then we want 80% of that, which is 51.2. And then 40.96. And then 32, I'm going to start to round. Decimal, well, 768, that's okay. And I'm going to leave it in my calculator, so 26.2. And then (32) 26.2, sorry, 20.97. Okay, so that's how much is left after a day. So when we're talking about first differences, what we're going to do is we are going to go up this column and we're going to subtract. So I'm actually going to just round these to the nearest one. So I'm going to go 21 minus 26 and I get -5. Okay, so I get 26 minus 33. And I get -8. Okay, 33 minus 41. And I get -10. And I'm going to keep going up. So I get -13, -16, and -5. Oh, -7, -8, -10, -13, -16, and -20. Sorry. Okay, so those are not linear, or those are not constant, therefore it's not linear. So first differences are gone, and now we go up the second column. So -5 minus -7, and I get 2. -7 minus -8, and I get 1. And if we keep going up this column, we're going to get 2, 3, 3, 4. Okay, therefore it's not quadratic either. But if we go up this column and we go back to the y column and we do 21 divided by 26, we're going to get 0.8. Then we're going to go 26 divided by 33, and we're going to get 0.8. And if you continue to do this going all the way up, 33 divided by 41, 0.8. Okay, and if you do this all the way up, you're going to get 0.8 the entire way. Okay, and then therefore it's exponential. Now we're going to do the same question, but we're going to work with the 200 for the initial value. Okay, so if you do 200 times, and remember it's going to be that 200 times 0.8 because it's a reduction of 20%. So because it reduces by 20%, there's 80% left. Okay, the next number is going to be 160, 128, 102, 82, 66, 52, and then 42. And those are just rounded, which is fine. Okay, now if you go up the Y column, you want to find first differences, we're going to go 42 minus 52, and we're going to get negative 10. We're going to go 52 minus 66, and we're going to get negative 14. And we're going to go all the way up. So negative 16, negative 20, negative 26, negative 32, and negative 40. Okay, these are not constant, therefore it's not linear. Now let's go up to second differences. So we subtract the first differences. Negative 10 minus negative 14, I get 4. Negative 14 minus negative 16, I get 2. Okay, and you go all the way up, you get 4, 6, 6, 8. Okay, therefore we can see that it's not quadratic either. But if you take this Y value and you go up the Y column and you do 42 divided by 52, you're going to get that 0.8. You do the 52 divided by 66, you're going to get that 0.8. And if you keep going all the way up, you're going to get 0.8 for the entire thing. Therefore, we can say, because the ratios are constant, therefore it's exponential. So what we just did was we used first differences, second differences, and ratios to determine whether a table of values is linear, quadratic, or exponential. So now what we're going to do is we're going to draw a graph of each of the populations, and we're going to use the same set of axes. So this is going to be bacteria life. Sorry, bacteria left. Okay, and then we're going to have number of bacteria. And then we're going to have the time in days. Okay, remember we're going in 7 days. Okay, and we're going to go ahead and graph each of these, and we're going to graph them in different colors. So why don't we do the first one in like a blue. So we started at 100, then we went to 80, and we went to just over 60, in the middle here. Okay, and it's going to look like this right here. Okay, so this is graph number 1. And then let's graph the other one maybe in green. And we're going to start at 200. And then we're going to go to 160. And we're going to go to 128, 102, 82, 66, 52, 42. Okay. And that one's going to curve like this. And it's going to be number 2. Okay. And that's how we would complete that. So we can see that this is exponential. We know that this is not linear, and we know that it's not quadratic. So what we just did was we used first differences, second differences, and ratios to determine whether a table of values is linear, quadratic, or exponential. So now what we're going to do is we're going to draw a graph of each of the populations, and we're going to use the same set of axes. So this is going to be bacteria life. Sorry, bacteria left. Okay, and then we're going to have number of bacteria. And then we're going to have the time in days. Okay, remember we're going in 7 days. Okay, and we're going to go ahead and graph each of these, and we're going to graph them in different colors. So why don't we do the first one in like a blue. So we started at 100, then we went to 80, and we went to just over 60, in the middle here. Okay, and it's going to look like this right here. Okay, so this is graph number 1. And then let's graph the other one maybe in green, and we're going to start at 200, and then we're going to go to 160, and we're going to go to 128, 102, 82, 66, 52, 42. Okay, and that one's going to curve like this, and it's going to be number 2. Okay, and that's how we would complete that. So we can see that this is exponential. We know that this is not linear, and we know that it's not quadratic. Okay, example 2. The chart below gives measurements to the amount of air pressure left in an air compressor tank with a slow leak. So when we're thinking about a leak, we're thinking about it starting at one number and then like decreasing. Okay, H hours after being inflated. So we have H hours, which is time, and then we have the pressure. Calculate the first differences and the ratios of the pressure column. What do you notice? So this one doesn't give you a situation in the sense where you have to think of the numbers. It gives you all of the numbers. So the first differences, we're going to go up this y-axis, or this y column, I should say, and we're going to subtract 2750 minus 2800. And we get negative 50. Okay, we keep going, we get negative 50, negative 50, negative 50. Okay, all the way up. Now, I didn't include, so we can see here that it definitely could be linear for sure. Okay, but let's calculate the ratios anyways. Okay, so if we did 2750 divided by 2800, we would get 0.98. And if we did the next two, we would get approximately, and these are just approximate, but they're like give or take, so it's pretty good. 0.98, well, it could also be exponential. Okay, so kind of which one is it? So A asks us to calculate the first differences and the ratios. What do you notice? So what do we notice? So the first differences satisfies. Okay, and then the ratios, okay, are also satisfied. So really what we're thinking, is it linear or is it exponential? Okay, it could potentially be either one. So this is just an example just to get you guys thinking. And B asks, the owner of the tank left the tank overnight, and after 14 hours the pressure was 2300 psi. Okay, so at 14 it's 2300. Which model predicts this pressure most accurately? Okay, so scroll down a little bit. What we're going to do is we're just going to pattern. So for linear, we left off at 5. Now we're going to go 6, 7, 8, 9, 10. Okay, and if we're going down by 50 each time, 1750, 2700, 2650, 2600, 2550. Okay, and now keep going. So this is a continuation. 11, 12, 13, 14. So this would be it, right? So 2550, we'd go down to 2500, 2450, 2400, and then 2350. So if you pattern down by 50 each time, like that, at 14, oh, 2500's here, 2450, 2400, 2350, 2300. I had to adjust that. That's one off. But it's definitely going to run into the 14, 2300. If you keep patterning down by 50, so therefore I would definitely say that this is linear. I would also say that it's linear because like linear works out perfectly. It's exactly -50 each time. But if you divide the pressures by one another, it's approximately 0.98. Some you have to round up, some you have to round down.